Karasek. This is Ruijsink. We're from the Delft University of Technology, from the Micro Vehicle Lab. So we work on various types of vehicles. You can, sorry for the screen size, but we work on everything from, let's say, quadrotors to quite large vehicles that are transitioning vehicles that can take off and land as a helicopter, as a multicopter, but then transition into forward flight and then fly like a fixed wing.
Let's monitor.
And that's a project Rick is going to talk about. But I'm going to talk about a project which we is focused on smaller vehicles and a project which is very bio-inspired. So it has wings that flap like in birds or insects. Let's see. So it's a project called Delfly. It has already been presented here at NEAT in 2007, I think. So I wasn't here back then. Yeah, so already quite some time ago. And at that time, that was the smallest flapping vehicle we have ever built, the Delfly Micro.
And this is HDMI.
Ruijsink that year won the best, the technical award for that.
Indeed. But over the years, we have built many different designs, ranging in wingspan from around this to the Micro, which was really small. Sorry, the other way around. So obviously, when designing these vehicles, we're taking inspiration from nature, but we're not making a one-to-one copy of an insect or of a bird, because of course our materials, our actuators are quite different to what you can find in nature. So we have to take some concepts from nature, but then adapt them to what works with the technology we have at hand. And of course, as a university, we also want to learn something about nature, and that's actually how I got drawn into building these vehicles. It was the curiosity, how insects fly, how birds fly. Now, sorry for the size of the video, but here you can see the typical Delfly wing motion. So basically, Delfly, it has two wings that are in X configuration, and they flap like this. They are overlapping, but they cannot really overlap my hands, so I show it one behind each other. And they do what we called a clap and peel motion. So basically, the two wings they clap together and then they peel. So they are very soft. They are made of very thin. This one is I think 10 micron thin mylar, but we use even a thinner one. And this actually mechanism, when the two wings clap together and they are peeling apart, they improve the thrust production and overall power efficiency of the system. And it's actually a strategy that you can see in some birds and insects, although it's questionable whether they do this, because basically that's how far their wings can go. So maybe they just want to increase the motion of their wings, and at some point they clap their wings, but they also do this. And it helps us to fly for a bit longer. Now, we have developed different mechanisms over the years how we can actually move the wings in this way. But this is actually the Micro, so the 10 centimeter wingspan Delfly we presented here in 2007. But you can see that the configuration still resembles an airplane. So we have the wings in the front, they flap, produce thrust force, but then you have a conventional tail, and that is actually giving the vehicle stability, and also has control surfaces for control. So you fly it like a regular airplane. The disadvantage is that you cannot go, you can fly quite slow, but you cannot really hover. With larger vehicles that have higher thrust, you can actually stop and hover. But of course your control authority is very limited then, because your tail surfaces rely only on the downwash. So our goal was actually to make a vehicle which is one step closer to insects or maybe hummingbirds. A vehicle that does not rely on its tail. I'm going to just skip this slide. There were some intermediary steps where we actually try to improve the control effectiveness by adding some additional surfaces, like you can see here, some sort of Arion, but you can also see that that's not a very elegant solution. So what we wanted to do is we wanted to get rid of these tail surfaces and make it fly truly like an insect. Now, an insect has no aerodynamically active tail, so actually to fly, it works a little bit like a helicopter. So the flapping wings, they produce a thrust force which is kind of body fixed. And if you want to fly forward, you tilt the body, and then the thrust force makes you fly forward. And the same if you want to go sideways. Now, of course, how do you make the body tilt? So insects, they can do many different things. They can flap their wings more in the front, more in the back. They can adjust the angle of attack of the wing throughout the stroke. And so they actually combine all these strategies. But yeah, we had to kind of just pick some of them, the ones which are dominant, because we want to achieve flight like that with minimum amount of actuators, to be as light as possible, of course. And our motivation was also because we have put a lot of time into developing the flapping mechanisms, which were very reliable, the wings which were power efficient. So we wanted to reuse most of the original flapping system. Now, when I will now talk about roll, pitch, and yaw, I will define it with respect to, let's say, hover position, which is for this vehicle in this orientation. So pitching is the same like in a fixed wing aircraft, but then rolling is this motion and yawing is that motion. And so for an insect, if it wants to roll, basically what you need to do is you need to increase the thrust of one wing pair compared to the other one. And so we thought, okay, for us it's quite difficult to change the amplitude of the flapping, but it's very easy to increase the flapping frequency, which is something an insect cannot do because its two wings are kind of linked. But we can do that, so we thought, okay, let's just take the flapping system we already had and use two of them, one for the left side, one for the right side. And then when we do that, we can actually connect them not rigidly, but using another actuator. So we can actually adjust in forward flight, that would be the dihedral angle, so we can move the wings more in the back or in the front, or up and down when you see it like this. So what happens is that your two wings are flapping like this, but then if you move them more in the back, you shift the thrust vector backwards, and then it gives you a torque that makes your body pitch forward. So this is how you actually tilt forward, and yeah, if you flap your wings more in the front, that will tilt you in the opposite direction. What is also nice is that, so the vehicle hovers like this, and if it wants to fly forward, it actually needs to push against the sort of air coming from here, so it needs to keep its wings flapping slightly behind. So it actually gives you also a dihedral angle that is stabilizing the flight. So there are two benefits of doing that. And so these two mechanisms allow you to roll and to pitch, so that's basically all you need to stay kind of stabilized. Of course, you still want to control the direction in which you fly. So we have a third mechanism that basically does vector the thrust of left wing pair and right wing pair in opposite directions. So you have the root of the wing, we just deflect it like this or like that. That takes the two thrust vectors, points them like this, makes you rotate like that, or the other way around. Now, yeah, it's a very simple concept. So in reality, we have the two flapping mechanisms. Each has a brushless DC motor, a gearbox, and a linkage mechanism, quite standard, that makes the two wings flap in opposite direction. They are independent. Then we have a servo in between. It's a Hobby King 5330, one which is, let's say, lies this with sufficient speed and power for this system. And there's a gear mechanism. So basically we have two arms which have gears in between. So if you connect your servo just to one of those sides, it will also make the other wing move. So the two wings then move synchronously. And another servo of the same kind that holds the wing roots and just tilts this little bar forward here, backward there. It's not exactly the motion we would like to have, but it's a very simplistic solution, and of course that saves weight, so that's what we use. So basically, the other way around. So this is basically what is shown on these figures. Now, to get a vehicle flying, you also actually need a small computer and sensors on board, because the inertia is very low, and it will rotate left or right very quickly. So, as a human pilot, you're not fast enough to actually correct for the vehicle, and you cannot make it passively stable. So you need a computer that is gonna do that for you. So we have on this vehicle, it's 1.5 gram board, which has 6 degree of freedom inertial measurement unit, so 3 degree of freedom gyros and accelerometers. But basically what they do, they estimate how your vehicle is oriented in space, and also they measure the rate at which you rotate. And these two values we're using to calculate how to adjust the motions of the wings such that the vehicle stabilizes. Now, there's not much wind, so I'm gonna try to fly it. And then I'm gonna tell you the whole story from the first flight test until how we got here. So, let's see. Of course, I expect that when I start flying, there is going to be a gust, but you can see, you can just hang in the air, and I can control it very precisely. There's a little bit of draft, so I have to roll left. And I can fly in any direction, so you can go sideways, forward, and backward. Of course, I can also yaw. It's kind of tricky to flatten, but you can also accelerate very quickly, so I can go from hover too far forward, flying back.
It's windy in here now.
Now, because it's so agile, you can actually also do some tricks, like flips. Now, there are some programmed in, but I'm not sure what exactly it's going to do now. Well, can you see?
Your helmet.
So I think this should be like a roll top. Let me see, okay. It can also do other tricks, but I think I'm gonna wait till we're in the gym where there's a little bit more space. So I'm gonna bring it back.
Great kid.
Come to me. We actually also use it to study avoidance maneuvers of flight, so now it's trying to avoid me. So yeah, the whole concept is, I think, quite simple, but yeah, it's still a complex system in a way.
Are those the famous Didal gears?
No.
Some of them.
Something
but,
different?
No,
I think the double gear is
basically,
Didal.
yes. The intermediate gear is based on an original Didal gear, but Daniel we asked for one with a higher pinion because we needed a little bit more height, and through his channels he could produce the same gear with a
nice.
higher, more height, and the rest is our own design, which is indeed injection molded, and we use that from the first or from the one of the, say, the third generation of the Delflies. Up to now we still have quite a box, but a lot of those gear systems have been used in many projects involving flapping wings. Even one version with, instead of 2 set of wings, 4 set of wings.
Wow.
So 8 wings in total, and all crazy things. A lot of research has been done on test benches in wind tunnels, where with laser Doppler anemometry or other PIV, particle image velocimetry, the whole flow field has been studied, and also, for example, when you put such a flapping wing on a force balance, you basically limit the motion of the fuselage, which is not really exactly correct. So we also have done flying tests in our open jet tunnel. It's a 258, say 9 by 9 foot open jet wind tunnel, where we actually completely free fly with the position feedback of the model, and we can do PIV measurements in the real flying condition, completely untethered. So there has been a lot of, say, input from our lab, also to the aerodynamics lab and the CFD lab, because with these PIV measurements, also the CFD people have more input in tuning their CFD models, because we are speaking here not about a fixed mechanics, a fixed surface, but a surface which is deflected under the load. So this interaction between the load, the shape, and the lift, at least, is important. And with these all those measurements we could have made due to the abundance of gears, etc. And the brushless motors are from India. The Chandras Kahar, he
Micro brushless.
micro brushless. They make the motors and have made also many variants in height and in windings. And in fact, the motor, we used to buy the complete motor, but now only the stator and the rotor, because the rest is integrated in this injection molding.
What is the commercial application of this device? Somebody must be paying
At
for
this
research.
at this moment as we speak, but
We're trying to change that actually. So
Yeah.
towards the end, I'm going to show you some possible applications.
Does the controller board have accelerometers? Is there active stabilization going on?
Yeah. So actually, that was quite a challenge to get all that working. So
And that's custom, right?
I have
That's
some
not
videos
off-the-shelf
here.
like controller.
No, this is a custom design. But I think that these days you can already get boards which could do this on the market, because in the last few years the micro quadcopter market has made a lot of progress, and there are many components you can buy off the shelf now. For components, so we have basically these brushless motors from microbrushless.com, MX3A speed controllers, flashed with BL Heli, so brushless. We can actually, when we fly, we can also log a lot of data, which was actually important to understand what's happening on board and how to get this vehicle flying. You could have noticed that there is quite a lot of vibration on board. That is partly inherent to the flapping wings, because you're not producing constant force, but it's a force that goes between 0 and maybe 2 times the weight. And on top of that, the concept we chose uses different flapping frequencies on your left wing player and right wing player, which means that when they are in counter phase, you can have quite a lot of vibration due to that. So the challenge there is to process the sensors. Well, first of all, to make sure that your sensor does not saturate. Because if your sensor saturates, that means we are not measuring directly the orientation, but we are measuring the rate with which you're rotating, and then we integrate that to get the attitude, the angles. But if your sensor saturates, then you cannot get the angles. So we actually had to mount the sensor on a little piece of foam that helps to isolate some of the vibration. And afterwards, we still do some filtering of these signals, such that the signals that you send to your actuators are clean enough, such that the actuator can follow that. This took us quite some while. Basically, what we usually do is we just put some sort of string to which the vehicle is supported, so that if we lose control, which happens all the time at the beginning, we don't damage the vehicle, and we can do enough tests. And having access to the onboard data is very helpful, because then you know exactly what was happening, what did the attitude, what was the attitude estimated on board compared to what you could observe. We also have a arena where we can fly with just a motion tracking system installed. So basically, that gives you the true attitude, and also you can measure how fast you're flying. So that was important for our research that we do with these vehicles. Around hover, we consume around 6 watts of power, and that allows to fly for around 5 minutes when we hover. But it is longer when you fly forward, because the system becomes more efficient because you're basically gliding, so you get extra lift from that. And the top speed is, I have quite a lot of slides here. The top speed is around 7 meters per second. Now, what is important when you want to design a vehicle like this is that you can control the 3 degrees of freedom independently. And they are not coupled, or they are coupled as little as possible. So if you want to roll, you need to be able to roll. If you want to pitch, you need to be able to pitch. And if, for example, when you roll, you will also pitch a bit, that makes your life much harder, and it's much harder to control the vehicle. And because the concept we chose kind of generates these 3 torques with very different mechanisms, you have a very nice decoupling, and that makes your life much easier. So basically, we are then running a PID loop for each degree of freedom separately. So you're measuring the rate, which is which you use in your D component, and then you estimate the attitude, and that angle is used then in your P core. I have some videos from the very first flight test. So we actually did attach a tail to it to improve to get it some passive stability. But it actually didn't go that well, so it was easier to fly without the tail from the very beginning. You can see. I don't know if you can see the videos, because is it okay? Yeah. Sure. So basically, we just support it on a thread, and then we just try things. If it doesn't work, we change the gains. It's a lot of trial and error. I think this was one of the first flights without a tail where it worked. So that's of course it's always the moment when you're cheering. But there were many things that were kind of difficult to understand related to the onboard vibration. So it took us quite a while to get all that right. These are just some gain tuning. This is something I have explained. So basically here you can see some of the onboard signals. So this is basically what would be sent to the actuators without any filter. So it's a very noisy signal. So we had to add some filter to make it a bit cleaner. But if you filter too much, then you get delays in your control system, and that will again destabilize the vehicle. So there is some, let's say, trade-off you have to make.
Are you filtering the sensor data as well?
At the end we decided to filter just the output of everything, but you could also filter the sensor data. I don't know if this video is visible, but you can see that although it looks kind of stable when you see it in real eyes, in slow motion everything is very flexible, but it's of course what you pay for keeping the vehicle as lightweight as possible. These are just some videos. We of course flew it outdoors. This is kind of semi-outdoors actually over here. You can fly it outdoors. It is sensitive to wind, so you need to be, if you have either outer loop that controls position, or if you're a fast pilot, you can keep it at one place. But because of the large wing surface area, it will get pushed quite quickly. So you need to orient your vehicle against the air for that. The top speed is, as I said, okay. Now, so let me just follow the order here. These you can see just some of the flips we were doing. You could see one here, and I'm going to show more flips in the gym tonight. To make a flip, basically it's an open loop program that we launch. So when we fly normally, we have the autopilot making sure that the wings are stabilizing the vehicle. But to do a flip, we actually pre-program it such that one of the wings flaps at its full power, the other one at low power. Until a certain moment, when we are somewhere here, we switch, and then the other wing flaps faster to decelerate the vehicle again. And when we are around this orientation, we again switch on the auto stabilization, and then it recovers. There is also a phase where we actually give some extra thrust to climb, because we lose a little bit of height when doing such a maneuver. Now, one funny thing is with brushless motors, you cannot go too low, because if you set the signal too low, the motor will actually stop. But then to restart it, it takes a random amount of time. So when we were doing the first test, we were trying to do one flip, but because of this delay, actually we did double flips because it took much longer. But it was kind of random, so yeah, most of the trials would end up with a crash. Yeah, we also can do a flip around the pitch axis using kind of the same strategy. And as researchers, we of course are also interested what the vehicle is exactly doing, so we can measure with an external motion tracking system the motion of the vehicle, but also on board all the signals coming to the actuators, and we can use that to create models of these vehicles. This is not really important. This is a test in the OpenJet wind tunnel. Here I fly it manually at speeds from around 2 meters per second up to almost 4. As you can see, I'm flying it manually, but it's secured with a string. And the faster you go, the harder it becomes to keep it in the jet. So eventually I lose control. But again, this test was useful because we could find the relationship between flighting frequency, forward speed in steady flight. You could do that outdoors, but then you don't really have a good estimate of your speed. If you do that in a flight arena, you're limited with space, so you very quickly at higher speeds reach the limits of your space where you fly. And this is a test showing the maximum speed, so transition from hover to maximum speed, which is around 7 meters per second. Basically, you just slowly increase your pitch command, so you tell it to pitch forward, and you just put maximum throttle, and it will go into almost horizontal flight. Thanks to gliding, you can even if your thrust points basically horizontally, will still have enough lift to maintain level flight. But for this test you need to adjust the gains a bit, because at higher speeds you need higher damping of pitch. This is just the same maneuver in slow motion, so you can really see that it goes in a split of a second, it goes into horizontal flight. yeah, we also do tests in the wind tunnel with a motion tracking system. So we have a motion tracking system that tracks the position, and we have a feedback loop that actually keeps the vehicle in the wind tunnel, and then we can do experiments like flow visualization. This is one of the very first trials where we just test the method out, but we fly in the wake of this cylinder. So it's an ongoing research. Okay, we also do some research into how actually flies fly with the help of this vehicle. I'm not going to go into details, but basically we could program the behavior or the, let's say, control actions of insects, of fruit fly in this case, which they do when you try to swat them. So a fruit fly is actually quite difficult to swat. If you try to do that, it's going to make this very sharp maneuver where it's actually rolling and pitching at the same time. And biologists, they had hypotheses how fruit flies do such a maneuver. We could program them in the robot, and because we know what the robot is exactly doing, we could kind of understand what was happening, and we could describe the dynamics of these turns, and even get some insights on aerodynamic mechanisms that help you to make such a sharp turn with a flapping wing vehicle. So I'm not going to go into details here, but maybe there is a video of such a turn here. So yeah, here you can see the robot approaching and then quickly turning right. And you can see that at the end it's going to kind of self-align with the direction in which it's flying. And this self-alignment is purely passive, so this is something coming from the aerodynamics of flapping wings. Yeah, these are just the data we're gathering when we do such experiments. And this is just a comparison of the trajectories we could get with the robot and with the fly, which are observed in flies for similar kind of settings. So we could really confirm that such a hypothesis is very plausible. And this actually is why our research was published in Science, and the robot was actually on the cover of the magazine. So that's a very prestigious thing, which we're very proud of. Now, yeah, you were asking a little bit about the applications. Okay, let me just go back. Okay, I have to launch this one. So, yeah, of course, one of the applications is in security. So we can mount cameras, but also different sensors on the vehicle. We can carry around 4 grams of payload while not decreasing the flight time too much. So here you can see a demo where we fly with an onboard camera. It's actually it's quite an old FPV system we used in this test, but it was more just to demonstrate the vehicle has this capability. And we also add autonomy to these vehicles. So we actually have a tiny camera system with processing, such that the vehicle can fly on its own and perform very simple tasks like following a line or flying through an opening like a door or window. So we took this vehicle to MAV competition IMAF, which was held in Melbourne last year, and we got the special prize for the unique design. And we're also looking into actually applications in the entertainment industry, and this is what me and Rick are pursuing also in a form of a spin-off of the university, because many people are actually asking us, okay, what is this useful for? But at the same time they're amazed and they like to see something flying like this. So we want to use this aspect of the flight, which is it's very natural. The sound is more close to what we are used to here in nature, and we want to use it in shows. So here you can see some videos of a newer system, which is much larger. So this is a 60 centimeter wingspan. The concept is similar to what we have here, but the idea is that we can build the system with much more robust components, and make it serviceable, easily serviceable, so that it can be used and operated frequently with maybe less skilled operators that they don't pay attention when handling things. So this is actually the first prototype flying, and this is a demo how such a show could look like. So it's just a first video we have with 3 vehicles flying with some LED lights that can illuminate the vehicles while we're flying. And the idea is to have, of course, larger swarms which are controlled autonomously. Now this is flown manually by people that actually flew this vehicle for the very first time on that day. So yeah, I think that's it for our flapping vehicles. If you have some questions, we can either do it now or after the talk of Rick.
Can do it now.
Yeah.
Yeah, so how does the efficiency compare, like in terms of duration per given battery, for you know, compared to a quad or a coax or some other platform?
So
There is a bottle of good whiskey here still available.
It's hard to answer, but if we look at it, let's say weight-wise, so this vehicle weighs around 30 grams, so I think it's 1 ounce. And if you look at a quadcopter of the same weight, the flight time is going to be 5 to 10 minutes maybe. So we're actually on par with such a system. Of course, we're a bit larger because we're just have larger wing surface, but in terms of weight, it's comparable. And I still believe there is lots to gain in flapping wings because there is just a few groups in the world that is researching that direction, and I think the aerodynamics are not fully understood, and there's really a lot to gain there. Also, insects, they for example use resonant bodies to actually improve their energy efficiency, while in our system there's some things that are flexing. What we did not really design any resonant system in it purposefully, at least, so I think there are still gains. The advantage is that if you fly forward, then you become more efficient than at hover, which is something you don't have to that extent with rotary wing. Another difference, that's something I will demonstrate tonight because I don't want to fly again, but because the wings, they move back and forth, if you're gonna hit an object, which happens especially when you fly indoors, it's not a problem for the stability of the vehicle, because the wing moves back and forth, it will just bounce off, but you don't lose control. If you have a rotary wing, like a helicopter, if your rotor hits something, it goes down immediately, and the same goes for quadcopters. So that's a big advantage, and also it's a safe vehicle because you don't have any fast spinning propeller. So this makes it very suitable for environments which are shared with people actually. So, yeah.
Fantastic. When you look at the flight characteristics of hummingbirds versus insects and other birds, how they compare?
Yeah, so hummingbirds are, I think, the best flyers, at least for me. And yeah, they're much better to what we can build now, of course, but that's kind of our goal. So have flight performance of a hummingbird. So being able to hover very precisely, but also fly forward at high speeds and being energy efficient.
How much? About $2.
For now, we cannot buy it, but that's something where we're looking into whether we could make it either a kit or a toy. But we're still hesitating whether that's the best direction to take. Yeah. But as I said, we're gonna look at applications in the entertainment industry first, and we'll see where it goes. Yeah.
Very nice.
And I would promise to tell something about what I'm now doing, also still at the university. But before that, a little bit more about the micro history. This is the Micromech Daisy, which is a model that I flew for the first time, I think, in 1996, and it's a simple design with carbon under pressure, so not not bent with a heat gun, but it's under pressure, and so it's one rod of 1 meter length, then glued together and with two small threads here and there. It is held in the oval shape, and also at these points, there is a brace wire to make the curvature, and through the tension in the wing, you get about a camber of 4% in the center, which flattens out to almost zero at the tip. And the carbon fuselage made from a carbon sleeve, and this model was used also as a test bed to develop the Micromech radio system. And here you see a picture of me holding, say, the main fuselage, and this was a prototype receiver, and here you see the microchip decoder that Bob Salmon has programmed. I could design electronics, but I was not a programmer, and I came into contact with Bob, and he said, I can do that, and what do you want? No. So then you write an email with requirements, and a few days later there came a package with the microchip programmed. I soldered it into the receiver, and so basically the receiver receives its pulses. Basically it's what we now call the S-bus pulse train, and from that I thought you could have one microprocessor that decodes that and sends out the information in the right way to the amplifiers for the magnetic actuators. So basically it mimicked a system that I made in discrete integrated circuits before. So it first decodes the pulse train, and then you have if the pulse is more than 1.5 milliseconds, the difference goes to one output, and if it's less than 1.5 milliseconds, it goes to another output that is amplified in a bridge, and that controls the magnetic actuator. And of course, the first microchip that Bob sent me worked, certainly, but of course it doesn't always work exactly as you like in the first time. So that went on a few times back and forth, so, and in a reasonably short time we came to a good program, and I still know that the last chip I got, which was okay, after my work I soldered it into the prototype receiver, and exactly I had a flight of 2 days, 1.5 minutes before 12 o'clock at night until 3.5 minutes after 12 o'clock, and I flew outside around a street light, and I could test that was good. And so Bob has been very influential in getting this done. Here is a flight of the Fike, a famous monoplane, no dihedral at all, controlled only rudder, elevator and motor, and it flew beautifully without ailerons and a flat but a very short low aspect ratio wing, then you don't, and a high wing, you don't need ailerons or dihedral at all. This flew very well. And then around 2002 I came into contact with Fred Marks, also because of the fact that I was working on a small brushless motor, and I had contact with the Philips factory that makes small brushless motors for the for CD-ROMs, etc. And I could get those bare stators and their magnets, their rotor, and wind it, as we all did. Rewinded the motor, and it was not good. And then changing the rubber magnets with real magnets, then became quite a good motor. But I only had an integrated circuit from Philips, which gave the output for the 3 phases, and you could it was either on off, or you could change the voltage level of the output part to change the RPM. And at that time there was no controller that was suitable for one cell, and I had a motor but not a controller, and I have written to almost every manufacturer of speed controllers, but there were already of course brushless speed controllers, to make a speed controller suitable for one cell. And the only that came back with a positive result was Jetty, and I still have the first prototype at home of the speed controller that worked on one cell and was only 3.5 grams, which was quite small for that time. But so we were progressing fast, as we have said before. But in 2002, Fred Marks had the idea to to buy the rights on that motor, and which didn't finally was pulled through. But he also just got a shipment from COCAM with interesting LiPo cells that were the first 140 milliampere hour 7C LiPo cells that he has got from COCAM, and he got them quite cheap because basically it was a mistake, those cells. They were made to be used in a Bluetooth system, but in the spec sheet the designer of the cells misread 1 decimal point. So he made it for much higher discharging currents than it was needed. So obviously the cell was too heavy and had too little capacity for that Bluetooth application. But for us it was the first usable cell, and so he got that, and then we came indeed. This is the comparison of a 3.7 gram LiPo and 3 50 milliampere hour NiCads. So 1/3 of the weight and 3 times the capacity. We know we came far. And this is one picture of a small coasters, beer coaster sized model that I've flown in 2003 at the first European conference where I was together with Alexander van der Wolstijne, where he flew his small helicopter.
Pixel.
The Pixel, yeah. He won the first prize for rotary wing. I won with the Daisy, basically the lighter version of the Daisy, where that was 11 grams total weight, and I flew and then put another 11 grams of lead on it, and it took off also easily. It still flew 20 minutes with that payload. And this was a fun flying disc. Now it flew the other way around. But I want also to talk a little bit about another project that I'm working on, is the Navy drone, which is basically stemming from another project where we participated also in 2016, but before and after also, in the Outback Medical Challenge, where the task was to take off autonomously and autonomously fly first a course of 25 kilometers, so about 16 miles, land there close to a person who was sitting there, and that had to be done autonomously on vision. We got the coordinates of the position with an accuracy of about 1,000 feet, and then you had to see with cameras or whatsoever where that person was, and you had to land close to him but not too close. We did that mission. We landed almost close to him, but just hit one tree and it crashed. But anyway, and that came mainly because of the fact that we had long range connection and iridium, and we were told that there was no Wi-Fi or no cell phone, no 3G or 4G available. So the long range was out of range then, and the iridium is satellite telephone was too slow. It takes many seconds before you get back your information, so we were too late to put an invasive action to save it from those trees. But anyway, we became second, because the first, they knew there was cell phone and they used that, and all the others were not as good as we. This is a biplane, a flying wing biplane, and with a big rotor and two tip rotors. It takes off vertically on with the big rotor, and the tip rotors cancel the torque out, and then it transitions to horizontal flight. And the model is about 1.60 meter span, and the rotor is 1 meter. It flies very well when everything goes well, and, but it is sometimes tricky because the effects. I'm not a dynamic skilled engineer, but especially not the rotor dynamics. But the rotor influence is sometimes in some conditions it's more like a helicopter, in other conditions it's more like a normal plane, and it was easy, except I don't know anymore, either in the right or in the left turn it could be critical. The rotor, I did design the rotor, and was made to have a good hover performance but also a good forward performance, and so the design was to have a very low pitch for hover and go to a very high pitch of about 4 meters pitch, which is feet, yard, inches, what do you want to? But say between the two poles for one revolution. So designed to rotate about 1,000 RPM in forward flight, which it was working, but only the dynamics of the model was too much reduced. When you fly nicely at a constant velocity, it has a good efficiency, but when you need to climb, you have to reduce the pitch, increase RPM, because it doesn't give you enough thrust without overpowering the torque of the motor. So there were some challenges with that system, but it flew. But it doesn't start automatically. Maybe it's not easy to see, but here it flies horizontal and it makes the turn, comes back, and for the now it goes into the transition soon for the landing, and you go up. And then land like a helicopter. This was the version that went to Australia, and I will go on. We use this system further and still are using it, and with this Delftacopter now we made the first official beyond BV loss, beyond visuals line of sight flight in the Netherlands, which was approved by all the Dutch authorities, and we went from mainland to one of the islands, also about 20 kilometers, and landed there. The control vehicle that we partly can use, it's owned by partly the Delft University and TNO, our Dutch technical research organization, and we use that as a communications vehicle, and it landed on the island. Okay, and but now we are working on a project which is sponsored by the Dutch Navy. We are working on it. I can't talk about it because it's an open challenge, and there are two more universities working on a project to take off from a ship on full sea and on a confined space on the ship, fly for at least 3 hours at a speed of at least 50 miles an hour and come back and land on the ship again. And we are encouraged to use hydrogen in this. Yeah. So that is an interesting challenge, I think, and we think. And again, I've been asked to make the aerodynamic and propulsion design. The concept was made with Bart Remes, who has been here in 2007, I think. No, not in. Anyway, and me made the concept, and I made the aerodynamic and the propulsion design. It's basically it's based on an existing man-carrying aircraft also with electric motors, where the wings, two of the same wings, they are like this, and the fuselage in between, and the fuselage is shaped such that it sits in rest like that, and it can take off vertically, and vertically it's like a hexacopter, or in this case 12. What is it?
Dodecacopters.
Okay. and in forward flight, it's basically a tandem. And
Who's flying that?
Somebody's got one going down.
yeah.
Fine.
Is that one of yours?
No comment.
So this one has 3 motors on each half wing, and this is a workhorse made of 2 multiplex foam models, and even 2 fuselages cut and fixed together. First ideas to see if it can work, and here you see another picture, and here if no, why? How do I make it run? Yeah. Yeah. Here it flies in our cyber zoo. You already yeah. We have we call it the cyber zoo, about what is it, 9 meters, so 10 yards, 10 meters, and 11 yards by 11 yards by 11 yards, equipped with I think 12 cameras, infrared cameras, and with the markers on the model, you can actually record what he is doing, and if you have your either the transmitter or the computer in the same loop, you can collect all the data, all the flight performance data from the model. And here the first tests were done on how it behaves, and so will it respond well enough to yaw, roll, pitch, etc. And we have flown this from the ship and on the ship. It is starting to be visible now. And it flies, so the ship has now tailwind, and it comes in on so backwards basically. It can also fly very well backwards.
Is this totally autonomous, or is somebody controlling?
We have made several fully autonomous landings and flights, but also manuals, and this is one of the first with the final prototype. Another model, as you've seen, and I will here is a picture. We have made several trips. This is one of the bigger ships.
2 years ago at Oshkosh at AirVenture, there was a similar design. It's a manned aircraft.
Yes, yeah. I was referring to that that plane and that was also one of the inspirations of us. And takeoff is easy. Here, people are working on the hydrogen fuel cell, and so the whole installation of the hydrogen cell is about 9 kilograms. So the total weight of the final version will be about 11 to 13 kilograms. And again here, this is the prototype as far as we have it flying now, but we are working on one. This will take about a maximum mass of 8 to 9 kilos, but we are now using some bigger motors. Okay, no. And one of the things is we have 12 motors which are used for hover and for the transition, and at a certain speed the 4 middle motors, they stop and have folding propellers, and only the 4 outer motors are used in forward flight. They are also rotating in the right direction so that they counteract the tip vortex, which gains about a little bit less than 10% in performance of the total airframe. Okay. So I'm now at the moment into something bigger, and for my hobby I fly slope soaring 3-meter gliders, 2 kilograms, and with full ballast 4.5. Yeah, that's another thing. Yeah. Okay. Any questions?